Hello, my name is Silvia Casacuberta, and today I will be presenting our work on complexity theoretic implications of multicalibration. This is joint work with Cynthia Dwork and Salil Vadan. The term multicalibration was first proposed in 2018 by Everett Johnson, Kim, Reingold, and Rothblum, and it was proposed in the framework of algorithmic fairness. Specifically, there has been a growing interest in the Theory CS community to use the tools and frameworks from Theory CS to advance the field of algorithmic fairness. One such technique that came from this effort is the definition of multicalibration, which informally asks that given a collection of subpopulations, which we understand as minority groups in this context, we want a multicalibrated predictor to ensure calibrated predictions for all of these groups in the collection simultaneously, hence the term multi. It's a natural notion of fairness that we would want to guarantee. And it has turned out to be a really, really fruitful notion in recent years. There's been an explosion of work in this area, and it's been shown to be useful both in practice, but also in theory. There's been really, really intriguing connections to other subfields of computer science, such as connections between multicalibration and loss minimization in the line of works of omnipredictors, on connections to forecasting and outcome indistinguishability. In this talk, we present a new connection from multicalibration to the field of complexity theory. Specifically, by viewing multicalibration as a strengthening of the so-called regularity lemma that was shown by Trevisan, Tulsiani, and Vadan in 2009, so preceding all the work on algorithmic fairness and theory CS for fairness, we obtained stronger and more general versions of some fundamental and classical theorems that also precede all of this line of work on fairness. In our paper, we focus on three classical theorems. First, Impagliazzo's hardcore lemma in complexity theory, which studies hardness of functions. Second, a theorem on computational characterization of pseudo-entropy in the field of information theory. And third, the dense model theorem in additive combinatorics, which played a role in the proof of the Green-Tau theorem, stating that there exist arbitrarily long arithmetic sequences of primes. Multicalibration allows us to obtain meaningful generalizations of these results. And so this provides us with insights in both directions, both into the power of what is multicalibration doing as an object, but also new perspectives into these classical results. So now that we've given a summary of what our paper is saying, let's start using some notation. So multicalibration is a strengthening of another notion that was also proposed in this original paper called multi-accuracy. So that's a weaker notion. And let's see what multi-accuracy is asking for. So we'll have a finite domain X of individuals, a collection capital F of functions, Boolean functions that in this context we understand as protected groups. Then we have an arbitrarily complex function G, and H is the predictor that we're building, which is supposed to be a good model for this arbitrarily complex function G. We say that H, the predictor that we are building, is multi-accurate with respect to this collection of functions F and epsilon if this condition is satisfied, the one you see boxed on the screen. What is this saying? This is saying that for every F in the collection of functions, when we look at the points in the domain in which F is saying 1, so you can see this as the points that this distinguisher cares about, we want that the expected value of G and H is very similar, so epsilon apart. And we want this to hold for every function F. So basically, this is saying that we don't want that a predictor to be good on average, but then when we condition on, say, women or some other group, then the accuracy drops. So this is a definition. Now the question is, can we build such an object? And they showed in the original paper that the answer is yes. So if you give me this collection of Boolean functions, the epsilon and so on, I can give you a predictor H such that H is multi-accurate for G with respect to this class F and epsilon. And also H is what's called of low complexity with respect to this class of distinguishers. I'll say more about what this means, but essentially you can think of it that H is not much more difficult to compute than the functions in the class F. But it turns out that this is exactly the regularity lemma that Trevisan, Tulsiani, and Vadan first showed in 2009. They said the exact same theorem in their case. It was nothing to do with fairness. It was a complexity theoretic result, and the point was to simulate a complex function G using a simulator of low complexity. And in their case, what I've been calling multi-accuracy, they called it indistinguishability with respect to F and epsilon. And this low complexity terminology, you can think of it as saying that if we say that H has complexity O of 1 divided by epsilon squared with respect to the class F, this means that we can compute H with a circuit that has S, where S is O of 1 divided by epsilon squared, oracle gates to functions in F, which in the context of the regularity lemma, we think of these Fs as distinguishers. And then we can put together these oracle gates in a low complexity circuit. And we will use a shorthand F of S to denote the class of functions that have complexity at most S with respect to F. So hence the drawing that you see on the right. The second really important point, after we have established the equivalence between the regularity lemma and the multi-accuracy lemma, is that the regularity lemma has many important implications. And in many different subfields of computer science, you can think of it as kind of a meta theorem that you can instantiate in different subfields. It has implications in graph theory with the Samredi regularity lemma, in complexity theory with Impagliato's lemma, information theory, additive combinatorics, cryptography, and so on. It has many other implications, such as Yao's XOR lemma. And in the original paper, they show that the regularity lemma implies, so you can show some of these theorems with using it. And so a natural question arises, which is, what happens to all these fundamental theorems if we use a stronger multicalibration theorem instead? And this question was studied concurrently by Dwork, Lee, and Tankala for graph theoretic implications, so for the case of the Friedrich-Anand regularity lemma. And we focus on the complexity theoretic implications. In this talk, I will focus on Impagliato's Harker lemma, but you can check out the paper to read our generalizations of the pseudo-entropy theorem and of the dense-model theorem. And so to conclude the setup that I've just explained, we have this equivalence between multi-accuracy and regularity lemma. I have just told you how the regularity lemma implies many classical results, where this first acronym stands for Impagliato-Harker lemma. And then we now have a stronger tool, multicalibration, that has been given to us by the fairness literature. And so the question is, what stronger notion do we get when we plug it into this diagram? Let me now define multicalibration formally. So we have the same notation as before, but now we say that a predictor H is multicalibrated with respect to this class F and epsilon if the condition that you see on the screen holds. And what this is saying is that before, for multi-accuracy, we're only looking at what happens when for F equals 1 for every F in the class F. Now we also condition on the values of the predictor H. So we look at the level sets of H, and we say, okay, when we condition on H being equal to V for every such possible value V, and on F being 1, I want the predictions to be calibrated. And what that means is that on expectation, the true values of the point, so G of X, actually equal V in expectation, where V is the value of the predictor on that area. And so this is a notion that holds for predictors, but notice that any predictor induces a partition by taking the level sets. So we can get directly a definition of a multicalibrated partition by taking the level sets of a multicalibrated predictor. And so we can restate this definition with the expression that you see on the screen, where we have just replaced H by V. We were looking at the level set of H anyways. But also it turns out that if you can build a multicalibrated H, you can always change it a little bit to make it still a multicalibrated H, but such that on every piece P of the partition, the value of H is exactly equal to the expected value of G on that piece. And so you can think of a multicalibrated partition as this partition of the domain into different pieces, such that on every piece, our predictor H equals the expected value of G on that piece. So this is a definition. Again, the question is, can we build such an object? And the answer in the paper by Avery Johnson et al. In 2018 is that yes, we can always find a low complexity partition that is multicalibrated. What do we mean by low complexity? We mean that there's not too many pieces in the partition. So in particular, we have O of 1 divided by epsilon parts. And then the function that maps each X to the corresponding level set dictated by H is an efficient function. And in particular, it's not much harder to compute than the functions in the distinguisher class F. So this is the similar notion as before for the predictor, but adapted to partitions. Okay, so now that we have the multi-accuracy and multi-calibration theorems, so that we know that the multi-accuracy theorem is equivalent to the regularity lemma, let's now look at one of these implications that I have told you about, is an important implication of the regularity lemma. And I will focus on Impagliazzo's-Harker lemma. Impagliazzo's-Harker lemma was shown before the regularity lemma. It was shown in 1995 by Russell Impagliazzo and later improved by Hollenstein. And it states the following. We're given a Boolean function g that is assumed to be delta weakly hard with respect to a class of distinguishers f of s. What does this mean? This means that for every single distinguisher in this class, so in this picture we have f1, if we look at the probability that f and g disagree, we're always going to find at least a delta fraction of the inputs in the domain where f1 and g disagree. Now we take another distinguisher, f2. We can again find at least delta points where the two functions disagree, and for f3, and so on. But of course, these delta points are distinguisher dependent. They're moving around the domain. And so the question is, if we have this assumption on the weakly hardness of G, is the hardness averaged on the domain, or is it somehow concentrated somewhere? And what Impagliazzo showed is that it is always concentrated somewhere. So if this holds, then there exists what's called a Harker set, which is a subset of the domain, such that G is what's called strongly hard on this Harker set. And this means that for every distinguisher in the class, this is a slightly smaller class of distinguishers, F and G will always disagree on at least 1/2 minus epsilon points. And so this is saying that inside of the Harker set, the function G is maximally unpredictable to distinguishers. To guess G, they might as well just flip a random coin and make that guess. And they will not guess G better than that. And also, the Harker set is of density at least 2 delta. So it's important to have this lower bound on the density of the Harker set. In particular, 2 delta is optimal. And it's interesting to note that the original theorem by Impagliazzo only achieved delta density, and it took 10 years for Hollenstein to show that the optimal 2 delta density can be achieved. So this is a statement of Impagliazzo's Harker lemma, and I have told you before that it's going to have a relationship to the regularity lemma, and I'll tell you how in a second. But let me also note that while most statements of the Harker lemma are written with sets, we can have an equivalent statement for distributions. And so instead of having a subset of the domain, we're going to have a distribution on the domain, such that when we sample according to that distribution instead of uniformly, then the function G is maximally unpredictable to distinguishers. And then we can equivalently define notion of density for a distribution. So Travis, Dentouzzian, and Vadan showed that the regularity lemma, which we can now call the multi-accuracy theorem, implies the Harker lemma. How does the proof go? Let me give you a sketch. So remember that we have the assumption of that G is delta weakly hard on X. Now we call the regularity lemma with this class of distinguishers in G, and we get back a multi-accurate predictor H. Now we define a Harker distribution using that predictor H. And the intuition is that we put more mass where G and H disagree. And then you can show that G is strongly hard with respect to the distribution, and that distribution is dense enough. Importantly, in the TTV paper of 2009, they only recover density delta, which is suboptimal. I just told you the optimal is 2 delta. In our work, we adapt the proof to obtain a stronger theorem than the Harker lemma. And let me tell you how the sketch of the proof goes. So very importantly, we're able to remove the assumption. So in our theorem, we're given an arbitrary function G, which is not necessarily delta weakly hard. It's an arbitrary function. And yet we're going to be able to extract hardness from this arbitrary function. How? We apply the multicalibrated theorem to get a multicalibrated predictor H. And then on every piece of the partition, so now we have a partition given by the theorem, we define a distribution that's going to turn out to be a Harker distribution on every piece. And we use this VP value that is given to us by the partition. Then we show that G is hard when you sample according to this distribution. And then we prove that a lower bound on the density of the distribution that depends on this parameter that we call the balance of the function, this BP that you see on the screen, which is the minimum of VP and 1 minus VP. And remember that VP is the expected value of G on that piece. And we call it the balance because it's measuring the closeness of the function g to 0 and 1 on every piece. And so the closer g is to 1/2, then the more interesting our result is, because both the indistinguishability and the density parameter depend on this balance. And importantly, when then we're able to recover the original Harker lemma from our Harker lemma plus plus, this is how we denote this stronger version that we get from multicalibration, we get the optimal 2 delta density parameter, which the regularity lemma was not able to recover. So this was a sketch of the proof. So what precise statement does this give us? So this is a statement of our stronger and more general version of the Harker lemma, which we call Harker lemma plus plus. And it says the following. We have this set of distinguishers of Boolean functions f, and we have g, which is an arbitrary Boolean function. Then we can find a low complexity partition such that for every piece in the partition, technically for every large enough piece in the partition, there exists a Harker set of density at least to be P, where P is the balance of G on that piece, such that G is strongly hard on that Harker set. And notice that both strong hardness and density depend on the BP parameter. In particular, the more imbalanced G is on a piece, the better bounds we get, the more hardness we get, and the better lower bound we get on the density. So you can think of it as saying that we find a little Harker set on every piece of the partition. And so the point is that we get an arbitrary object, but we can decompose it using this partition to extract maximal hardness from it. To put it together, so these are the differences between the original Harker lemma and our Harker lemma, the stronger Harker lemma that we get through multicalibration. And as I told you, we are also able to recover the original Harker lemma from our stronger version. How so? Well, if we bring back the assumption that G is delta weakly hard, then you can show that on average on the partitions, G is not going to be too imbalanced. In particular, it's going the average balance on the pieces is going to be at least delta. And that's because you can show it by contradiction. Otherwise, if we took the constant function 0, 1 on every piece, depending on whether VP is less or more than 1/2, we could construct a function that predicts G too well, contradicting the delta weakly hardness of G. Then you can show that having this lower bound on the balance of G on average, when we glue the Harker sets together, we get a global Harker set that is at least 2 delta dense, which is the optimal Harker density. And so in the plus plus version, we have all these little Harker sets on every piece that we can find for an arbitrary function G. But when we bring back the assumption of G being delta weakly hard, we can glue the Harker sets to get this global Harker set. And the remark is that Reingold, Trevisan, Tulsiani, and Vadan gave a partition-based formulation of the Harker lemma, but they still had to assume that G is delta weakly hard, and their partition is of exponential complexity. And we discuss more in the paper the relationship to their formulation of the Harker lemma. Okay, so to finish, I will give you some more intuition on why multicalibration has something to do with indistinguishability, and to try to answer the question of how is it possible that we extract hardness from an arbitrary Boolean function. This brings us back to Yao's pseudo-randomness unpredictability equivalence from 1982, in which Yao said that to be indistinguishable from the constant 1/2 function is equivalent to saying that G is strongly hard, so maximally unpredictable. So if we compare multi-accuracy and multicalibration, if you look at the definition of multicalibration, you can read it as saying that we have found a partition such that G is indistinguishable from the constant function VP on every piece. And so you can look at a multicalibrated partition as saying G is indistinguishable from a Bernoulli of parameter VP on every piece. And so it's actually giving us indistinguishability for free. Because what happens is that when you look at Yao's equivalence, there's nothing special about 1/2. We can generalize this to any value VP in the range 0, 1, which is precisely what multicalibration is giving us. And so in our paper, we characterize multicalibration through these different indistinguishability-based notions. And so we say, if G is indistinguishable from the constant function V, what can we say indistinguishability-wise? And we have different ways of expressing this equivalence. In particular, one of them is one that gives us another proof of our more general version of the Harker lemma. And the point is that we can define the hardcore distribution to balance the V value, which is the expected value of G according to the original distribution, back to a half. And then this 1/2 is the 1/2 that we need for strong hardness, which is the one that's required by hardcore lemma. And that's how we get hardcore sets. So this is the multicalibrated partition that we get by calling the theorem. And you can see that on every piece, our predictor is equal to the expected value of G on that piece, VP. And this is when sampling uniformly, but then we can define a hardcore distribution on every piece, HP, such that when we sample according to that distribution, the expected value of G on every piece is 1/2. And this is precisely what allows us to have little hardcore sets on every piece. And in the paper, if you check it out, we unify our results through this lemma that I told you characterizes indistinguishability from a constant function in different ways. And the point is that the multicalibration theorem implies the assumption of this lemma on every piece. So it holds on every piece. And what does this tell us? We have different ways of expressing this. And what's nice about this unifying lemma that we have in the paper is that the 3 main results follow from this lemma. So I just told you how the 4th bullet point is going to imply our stronger version of the hardcore lemma, but also we get a stronger version of the dense small theorem through the 3rd bullet point, and we get a stronger version of the theorem characterizing pseudo-entropy from the 1st bullet point. And we also added the 2nd bullet point, so you can compare it to Yao's lemma. And interestingly, that's the direction, it doesn't go in both directions, unlike Yao's lemma. And so this is a unifying picture of how multicalibration relates to these fundamental and classical theorems that we have described in our paper. And also, if you read the paper, you'll find a lot of common themes across our 3 main results. So the hardcore lemma, pseudo-entropy, dense small theorem. We obtain stronger versions of the 3 of them. And the way the proof they have a lot of common themes. And so all 3 reproduce the original theorems locally on every piece of the partition, but such that when we bring back the original assumption and we glue things together, we recover the original theorems. All of our theorems, very importantly, remove the original assumptions. So all of the hardcore lemma, the Pame theorem, which is what we call the pseudo-entropy theorem, and the dense small theorem, which is the DMT here on the table, the original theorems all have an assumption. In our theorems, thanks to the multicalibrated partition, we're able to remove this assumption, and the theorems work for an arbitrary object. Also, interestingly, the object changes across these theorems. So in the hardcore lemma, we have a function. In the case of the pseudo-entropy, we have a joint distribution. In the case of the dense small theorem, we have sets. But no matter the object, the original theorems had an assumption on them, which we remove. And then another key insight is to separate the hardness from the density. And that's one of the key ingredients in our proofs that allows us to get stronger versions. And so we can still get density guarantees using the balance of the objects. And then when we glue things together, we recover the original theorem, which is what the table is summarizing. So to wrap up, we have seen how through the connection between multi-accuracy and the regularity lemma, when we go through multicalibration, we can obtain stronger and more general versions of fundamental and well-established theorems across different areas of computer science: complexity theory, information theory, additive combinatorics. We have also reproved the original theorems using the recent tools from algorithmic fairness, but we have obtained stronger and more general versions. And so this provides new insights into both the notion and the power of multicalibration. And I've told you how it is a really useful tool for indistinguishability related purposes. But it also gives us new insights into all complexity theory results. And in particularly, it sets forth this idea of you don't need to start with an assumption. You can start with an arbitrary object and then find a partition of the domain that allows you to maximally extract the property of interest. So distinguishability, hardness, and so on. And so this establishes new connections between the fields of fairness and complexity theory in a way that we hope will bring a lot more other fruitful relationships. Thank you very much for listening.